In this lesson, we are going to talk about the meaning of continuity in calculus. Let's review what we have done through some examples so far. Let's find limit of 3x plus 2 as x approaches 2. We know there are different ways to find this limit. One way is concept of limit. When x is getting close to 2, 3x is getting close to 6, and 3x plus 2 is getting close to 8. The other way is using properties of the limit. Limit of addition of two functions is addition of the limits. Therefore, the given limit is limit of 3x as x approaches 2 plus limit of 2 as x approaches 2. Limit of 3x is 3 times limit of x as x approaches 2, because limit of a constant times a function is that constant times the limit of the function. Limit of x as x approaches a is a, therefore limit of x as x approaches 2 is 2. Limit of a constant as x approaches a is that constant, therefore limit of 2 as x approaches 2 is 2. This limit is 8. You can set a table of values and find this limit. Let's find limit of square root of x minus 2 as x approaches 2 from the left side. As x approaches 2 from the left side, this limit does not exist, simply because x cannot be less than 2 in this function. Therefore, limit of square root of x minus 2 as x approaches 2 does not exist. Let's assume f of x equals x2 when x is greater or equal than 1, less than 1, 3x. Limit of f of x as x approaches 1 from the right side. We have to follow this rule, x2, because x is greater than 1. It's the same as limit of x2 as x approaches 1, which is 1. Substitution method. Limit of f of x as x approaches 1 from the left side. In this case, we have to use 3x as the rule of the function, because x is less than 1, and this limit is 3. Right side, left side limit both exist, but they are not the same. Therefore, limit of f of x as x approaches 1 does not exist. We know limit of a function as x approaches a exists if and only if both right side and left side limit exist and they are equal. Let's define continuity. Our approach is informal approach. We say f of x is continuous at x equals a, where limit of f of x as x approaches a is the same as f of a. This means function f of x is continuous at x equals a if and only if limit of f of x as x approaches a exists and it is equals to f of a. If a function is continuous, right side limit and left side limit are both equal to f of a. Let's have a quick example. Is f of x equals x2 when x greater than 2, smaller than 2, 2x, continuous at x equals 2 or not? f of 2 is 2 to the power of 2, 4. limit of f of x as x approaches 2 from the right side is limit of x2 as x approaches 2, which is 4. And left side is limit of 2x as x approaches 2, which is 4. All three of them are the same, therefore f of x continuous at x equals 2. To understand the meaning of continuity, let's discuss a little bit about discontinuity. There are three types of discontinuity for a function. The first one is when function is undefined at x equals a, and x equals a is the asymptote of the function. At vertical asymptote, function is discontinuous. When f of a is undefined, you may have limit of f of x as x approaches a. This means limit of f of x as x approaches a exists, but f of a does not exist. This is what we call a hole on the graph of the function in advanced functions. In this case, the function is discontinuous, and it's called removable discontinuity, since we can define the function by assuming f of a equals to the limit and make it continuous. When right side and left side limit of the function at x equals a are different, then it is jump discontinuity. It's called non-removable discontinuity. Therefore, there are three types of discontinuity: asymptote, removable, and non-removable discontinuity. Let's have a couple of examples. F of x equals 2x plus 3 when x is not 4. When x is 4, it is 12. F of 4 is 12. Limit of f of x as x approaches 4 is the same as limit of 2x plus 3 as x approaches 4. We use substitution method and we find this limit. It's 11. Limit of the function and the value of the function are not the same. Therefore, the given function is discontinuous at x equals 4. If we redefine the function and assume f of 4 is 11, then function would be continuous. The next example, f of x equals x2 minus 4 over x minus 2 when x is not 2. F of 2 is 5. F of 2 is 5. Limit of f of x as x approaches 2. If we factor and reduce the function, that would be the same as limit of x plus 2 as x approaches 2 equals 4. Again, since the limit and the value are not the same, function is discontinuous at this point. These two examples are examples of removable discontinuity. Next example, f of x equals 2x plus 1 when x is greater or equal than 0. When x is smaller than 0, it is x2. F of 0 is 0 to the power of 2. Equal sign is here. F of 0 is 2x plus 1, which is 2 times 0 plus 1. It is 1. Right side limit, we use the rule when x is greater than 0, 2x plus 1, and this limit would be 1. So far, the right side limit and the value of the function are the same. We say function is continuous from the right side. Limit of f of x as x approaches 0 from the left side, we use x2 in this case, and it is 0. The limit does not exist because the right side and left side limit are not the same. Function is discontinuous at x equals 0. As I said, it is continuous from the right because the right side limit and the value of the function at 0 are the same. Next example. Clearly, x equals 3 is the vertical asymptote of the function. When x approaches 3 from the right side, the limit is positive infinity, and when x approaches 3 from the left side, it is negative infinity. When x is a little bit more than 3, it is positive. The denominator is getting smaller and smaller, therefore the function approaches infinity, positive infinity. When x is smaller than 3, x minus 3 is negative, and the limit is negative infinity. So we have an example of discontinuity when we deal with vertical asymptote, jump discontinuity, and 2 examples related to removable discontinuity. We say function f of x is continuous on an interval, an open interval, if it is continuous at every single point on that interval. It is continuous on a closed interval when it is continuous on the open interval, a and b, and continuous from the right at a, continuous from the left at b. Let's have one more example. F of x equals ax when x is greater or equal than 3, less than 3, 2x plus 5. F of x is always continuous. It is continuous on real line. Find the value of a. As you see, for x less than 3, the function is a linear function. It's always continuous. For x greater than 3, it is always continuous too because it is linear. Therefore, the only point that we need to make the function continuous in order to have it always continuous is x equals 3. Left side limit of the function at x equals 3 is limit of 2x plus 5 as x approaches 3, which is 11. Right side limit as x approaches 3 is 3a. 3a and 11 should be the same. Therefore, if a is 11 over 3, function is always continuous. Notice that polynomial functions are always continuous. Rational functions are continuous when the denominator is not 0. The function in form of irrational function with odd indices are always continuous. With even indices are continuous when on the radical is positive. Thank you.